So I've showed this slide in previous episodes, but I always keep coming back to it because it's so important. If you actually go around and look at agricultural communities across the country, and I come from one, and actually two, as I spent my childhood in two different regions, you have insect resistance, disease resistance, flavor decline, crop yields, crop diversity, watershed health, species diversity, and human health all start to decline in certain ways when agricultural systems are unpacked the way that we're currently using them. It may be subtle, it may only show up here or there, or in a certain crop that can't be grown in a region economically anymore, and then it gets shipped over to be grown in another country, or there may be a nonstop disease for 1 year that takes down 30% of the crop in a particular bioregion. All of these things have been experienced by farmers all across our country. If you look at the story of citrus greening in Florida, or if you look at some of the apple regions of upstate New York and New England that aren't growing as much anymore. If you look at the vegetable growing regions of the Pacific Northwest, where a lot of that production has been pushed south to Mexico or eastern into the arid regions. All of these things play a factor in the quality of life of those of us that eat food from our local farmers or farmers within our country. And so it's to this point that the Apical was founded. It's the entire reason that we exist. When we first came out with our leaf sap analysis in 2017, it was a very niche market, a very niche tool. Very few growers were catching on, and before you knew it, by 2020, thousands of samples per month were pouring into our lab from all across the country and countries internationally. Word has spread that there is something to leaf sap analysis. People have started to figure this out, that it's a tremendous management tool that was forgotten over 60 years ago. Similarly, water-based soil analysis are also showing common threads with leaf sap analysis. And so water-soluble soil analysis methods are regaining favor within certain agronomists in certain regions. They've realized that the acid-based soil extractions, while valid and precise, have limitations. When you're also looking for carbon analysis, and this is something we've touched on in previous episodes, the state of the art for many, many years has been only looking at total organic matter in a soil as an indicator. Now we have the capability to really peer into the soil and look at carbon as a resource for both microbes and plants. And if that carbon is deficient in a soluble way, we can work with that and use that as part of our fertilization program. As many of you understand and have noted during the previous episodes, carbon is a key component of the framework of the new paradigm of crop nutrition. Without it, you can't have the new paradigm. This is a key layer in the analysis of what we're doing here. We've also prepared a number of deluxe analytes, which we'll touch on in a minute, that delve into the metabolite of the plant and how the plant is intaking certain nutrients and metabolizing them into other molecular compounds. And last but not least, the EC of a soil when you're doing fertilization. If you have good EC in your soil, you're going to have good fertilization. But if you have your EC that's too high, your plant's going to be under one type of stress. If your EC is too low, it's going to be under a different type of stress. And so balancing the EC is a key layer in this process. And so here, what we have is our deluxe analyte list and how to unpack it and use it as an indicator of a number of different types of plant stress. So if you come to, so backing up a second, if those of you who are new to the game, we released a new suite of 14 additional analytes for our leaf sap analysis last spring. We also added the same analytes and a couple of additional ones for our soil analysis as well, bicarbonate and soluble carbon. So starting from the bottom and moving up, like I was just mentioning, the soluble carbon shows you what's happening as a microbial food source and helps you to plan the appropriate amounts of carbon-based fertilization. If you look at the bicarbonates in the soil, then you can also understand how much calcium is being immobilized by the soil as it exists today. This helps you to understand how much organic acids need to be put onto a soil to help release the calcium and tie up additional sodium and help you to design applications for that soil environment to use salinity reducers. When we test for ethanol in the leaf sap, we're testing for amino and polypeptide absorption within the plant cells. And this has a direct relationship to biotic susceptibility as studied through multiple research journals. This input category that we find here can help us to use a variety of peptides or amino acids to help supplement the plants at a given stressed stage during their growth life cycle. Next in line, we have a whole range of heavy metals. And now they're generally classified as heavy metals by this chart, but we include cadmium, chromium, nickel, lead, mercury, arsenic, titanium, vanadium, and there's maybe tin or one or two others. We find that, and this is supported by scientific research, that the functionality of the plant to reproduce and produce new cells is damaged when the plants are under metal stress. But this can be alleviated very easily and swiftly now, as there's a number of silicon and soluble silicon, and silicon dioxide products on the market. Using these intelligently in situations where plants are under metal stress is a key layer in optimizing plant performance. Total phenols can help you to identify where plants are upregulating their own immune system and if they're under a significant amount of abiotic stress. When you see polyphenols in the average range, that's a good sign. When you see polyphenols extremely high, oftentimes the plants are under stress. Now, some plants, for certain reasons, are desired to be under specific stress. Those polyphenols may be extremely valuable to the end producer of a specific category. But that doesn't mean that the plant needs to be under stress to produce those polyphenols. We've seen that plants can obtain high levels of polyphenols and extremely healthy growth not under stress at the same time. When we look at free amino acid, we find that plants are typically under osmotic stress. They have issues with their cell wall integrity and require osmoprotectants. When plants have high levels of or excessive levels of total protein, there's a problem with molecular stress and is indicative of a need for a systemic acquired resistance approach to that particular cropping system. Carbon is king. Thanks again very much, and look forward to seeing you all next week. Take care.